Alright, in this video, just like I mentioned in the previous one, we are going to be looking again at exponential functions, but this time we're going to be fitting these exponential functions, or we're going to call them exponential models, to tables of data. Now, an exponential model versus an exponential equation essentially means the same thing. It's just that when we're dealing with a story problem and real-life examples, most times data does not fit to a perfectly straight line. And so the equation that we come up with is not going to be a perfect equation all the time, where it's not always going to give us points that are always from the set of data that we're working with. And so that's why we just call these models. So we're just modeling the data. It's not exact. It's kind of like if you're putting together a model airplane. It's not an exact airplane, it's just a model of the actual one. Alright, so let's look at this story problem. It says in Huntley, Illinois, had been a small farming town, but when a large housing development was built, the population growth pattern changed. Two special censuses gave village planners a date in the table at the right. So we see that in 2003, the population was 12,270, and in 2005, it grew to 16,719. Now, in part A, it says find an exponential model for the data. Let P of t be the population t years after 2000. Okay, so our time, the values that we're going to be using here, we want to use the years after 2000. So instead of the year 2003, to make this a smaller number to work with, we're going to change this to be 3, because that would be 3 years after 2000. And 2005, obviously, would be 5 years after 2000, so we're going to use 5 there instead. Now, this process is the exact same from the previous lesson. Now, we did a bunch of examples. We did like 3 different examples like this. So that's why I already have this up on the screen. So you can just see the process is the same. Just to review, you always start with the coordinate with the largest x value. So in this situation, the coordinate with the largest x value would be this one here, where x would be 5 and our y value, our population, is 16,719. And we would divide those. Remember, we subtract the exponents. So when we're dealing with b to the 5th and b cubed, when we subtract those exponents, we'd have b squared. So we would have to take the square root of 1.36259, which would give you our b value of 1.167. And then we would use that value along with one of the coordinates. It doesn't matter which one you use. Personally, I just used the first one there because we have a smaller x value. So I used a 3 and the 2,270. You could have used the other coordinate. Now, and I'll talk about that in a second, but you're just going to get a slightly different answer. But when you plug 3 in for your x and 12,270 for your y and our b value, in this scenario, we would get an a value of 7,714. Now let's talk about if instead we had used the different coordinate, if we had used this one instead. I'm just going to tell you that you would get a slightly different value for a. And that's all right. That's why this is a model. So just know on a quiz or a test, if we had a problem like this, I will either tell you which coordinate to use to find the value of a, or I will know that there's 2 different answers and I will have both answers being correct. So you don't have to worry about that. Part B, then, it says predict the population of Huntley in the year 2015. Now again, we're going to use, remember this equation is based on the fact that our population, or t, our years here, represents the years after 2000. So if I were to use 2015 as my value for x here, I would get a huge answer, and that answer is going to represent 2015 years after the year 2000. So it would be the population technically in the year 4015. So we got to be careful when we want to answer these questions. So we want to use 15 as our value for x. And then in this situation, this scenario would get 78,224. All right. So again, that is just mostly review of what we did in the previous lesson. Now, sometimes we're going to use a calculator. So I'm going to show you how to do this on a graphing calculator. So here we have a table of values giving the different years and the number of breeding pairs of eagles that we had in those years. Now if we look at this part A, it says use a graphing calculator to fit an exponential model. Let x be the years after 1960. So if you notice, I've converted those years to be the years after 1960. So we're going to create a model using our graphing calculators this time for this data. So let's see how to do that. So the first thing we're going to do is we're going to go to a spreadsheet. So on your home button, go down here to where we have this middle button here for your spreadsheet. Now the first thing that we're going to do is we have to label our columns. You can label your column year if you want to type in the letter year, or type in the word year, or if you want to just use X and Y, we can do that. So if we type in X, And we're going to go over here and type in a y. Now we're going to put those values in for x. We have 3, 14, 26, 36, and 46. Remember, these are the years after 1960. Then we're going to go over here for a column y and put the breeding pairs in. So we'd have 417 pairs of eagles, 791, 1,875. Make sure you put the numbers in correctly. 5,094 and 9,789. Now, after you type in this last number, it's really important that you hit enter. If you don't hit enter, and if you go to the next step, and if you get an error on your screen that says that there's a mismatch error, you want to go back to this tab. And the reason why you're getting what's called the mismatch error is because it doesn't recognize that you put any number in here. It recognizes that there's a value here for x, but no number for y. So once you hit enter and move that cursor out of that, then it recognizes that there's a value there in that cell. Okay, so the next thing we're going to do is create a scatter plot for the data. So we're going to go over here to our home button again, or the on button. Don't go to the graph here. We want to go to this pink button, which looks like a bar graph. And we're going to create a scatter plot. Now remember, we could move our cursors to the left or right. Otherwise, the quick way to do this is just to hit the tab button. So if we hit tab, and then we select x for the x-axis, hit tab again, select y for the y-axis, and now we can see that this looks like an exponential set of data. So now to get our equation here, we're going to do what's called a regression equation. So we're going to do menu, analyze, regression. Now there's all these different options, remember. Now we want to find the one that says exponential, which is going to be down here, option 8. So here we have our equation. Now what we're going to do is we're going to round this. Sometimes they might say to round the a value, but to be more precise when we want to make predictions, it's always good to have some numbers past the decimal. So we're going to round this to 3 numbers past the decimal. So this 6 we're going to round up to be a 7. And over here, this 8, since after the 8 is a 4, this 8 we're just going to leave as an 8. So it'll be 1.078. All right, so let's go back to our notes. So we can put that in here. So that would be your equation. Now it says in part B, identify the initial amount, the growth factor, and explain their meanings. And so for this, even though we know we're not going to have a decimal amount of eagles, so we can estimate that to say that there was approximately 300 breeding pairs of eagles, or we can say the eagle population was about 300 breeding pairs, and it's been increasing by 7.8%, increasing by 7.8%. Now you might be saying, well, wait a minute, where do you get 7.8? Why wouldn't we say 1.078, or why wouldn't we say 178 or 107.8%? Remember, so basically we're doing the reverse of what we talked about in the previous video. We had 100% of our previous amount of eagles, so we're trying to figure out how many are we growing by, what are we increasing by each year, and so we're adding to that 100% another 7.8% every year. So the way that we'd phrase it is we'd say it's increasing by 7.8%. All right, now letter C is a review of earlier in this chapter about residuals. Remember, residual is the observed amount minus the predicted. And the observed is the value we get from a table or from actual collected statistics or actually collected data. And the predicted is where we use an equation or a model to come up with a number. So if we want to find the residuals for the years 1986 and 2006, well, let's start with 1986. So we would take to find, well, we know the observed in 1986, if we look at our table, was 1,875 breeding pairs. And so we want to figure out, well, what would our model give us for that year? So remember, we would use 26 as our value for x, because 1986 is 26 years after the year 1960. And when you do that, we would predict that we would have 2,116 eagles. And so that's a little bit more than what actually happened. And so when you take 1875 minus 2016, we get a negative 241. So what that means, the way that we can interpret that, is that was 241 less eagles than what we predicted. Okay, so that's a bad thing, because our predicted value was less than what actually happened. And so in this scenario with the number of eagles, that's not a good situation. But in 2006, let's look what happened there. So again, 2006 would be 46 years after 1960. So we'd put 46 in for X. So we'd get a predicted value of 9,502 eagles. Well, in 2006, there's 9,787 eagles, or breeding pairs of eagles. And so in this situation, we had more that actually happened than what we predicted. And that's a good thing in this scenario. So we'd have 285 more than we predicted. So that's how we would do that. All right. The last thing we're going to talk about in this video is this idea of half-lives. And so basically, so everything here that's highlighted, you want to make sure that you get in your notes. This is brand new material that's different from what or slightly different from what we did yesterday. It's just taking and applying exponential equations here to this idea of a half-life. So what a half-life is, it's the amount of time it takes for a radioactive element to decay to be half of the original amount. And so we're going to use this formula. So those of you that have our textbooks, so EVA students, those of you that have our textbooks, this is not in the textbook. Okay, so the way the book does it is way more complicated than what it has to be. So let's use this equation. So A, the capital letter A, represents a total amount left after a period of time. Then we have our lowercase a, which represents your initial amount or your starting amount. And T is going to be the total amount of time. And N is going to be the length of the half-life. So make sure you pause the video and get that in your notes. So let's look at this scenario. Here it says in 2007, the element polonium was in the news when London police detectives investigated the poisoning of former Russian KGB agent Alexander Litvinenko. And if you Google him, you can see all about this and how this all came about. But since polonium had never been known to be used in poisoning, the authorities did not look for evidence of it until weeks after the crime had taken place. As a consequence, they had to work backwards from the evidence to calculate the amount of polonium used on the victim. They made use of the fact that the half-life of polonium is 138 days. So here we get to do some investigative reporting. So we know that detectives in the investigation found polonium on a cup in a hotel that he had visited. Suppose that 4 micrograms were found, and it had been 30 days since he was there. Find out how much polonium was on the cup originally. So we're going to figure out how much was originally used to try to poison this Russian KGB agent. All right, so what do we know? We know the total amount that was found later. So this is not the initial amount. This is the total amount that was found later on was 4 micrograms. So we'll just use 4 there. And the time that had passed since then was 30 days. So we're going to use our time as 30. And N is the length of the half-life. And the half-life of polonium is 138 days. So N is 138. So we're going to plug all that into our equation. So we would have 4 equals A, which we're trying to find. And since we're dealing with a half-life, our growth value, by the way, will always be, our growth factor will always be 1/2. And then we're going to have, our T is 30 divided by 138. Now, this piece here, our calculator, we can do that all in one step. So if you plug that in your calculator, we're going to get approximately 0.8601. So we want to use more numbers past the decimal than maybe what we'll need in our answer. So we're going to use 0.8601. So if I divide both sides by 0.8601, we get what our initial value would be. When we get approximately we can round this to the nearest 100, 4.65 micrograms would be our answer. So if we wanted to come up with a model to represent the situation, we would just use our value for A now, which is 4.65. So we would say that our total amount would be 4.65 times 1/2. And then our T is always going to be, anytime we want to come up with our model, our time is going to be our variable. Because we know the half-life is for polonium is 138 days. So now we could use this if we wanted to figure out how much would be left after 60 days. We could put 60 in for your time. So that is our model. All right. I want you guys to use, again, that general form, this one here, to answer this question. So this one here is a little bit easier, actually. It says a certain substance has a half-life of 24 years. If a sample of 80 grams is being observed, how much will remain in 50 years? So they give you everything we know, or everything we need, rather, to find out what we want to know, which is the total amount. We want to figure out how much will remain in 50 years. So in this problem, we're trying to find the capital letter A. So that's what we're trying to find for this last example. So I want you guys to pause the video, plug the numbers into that equation, and find out how much would be left after 50 years. All right, how did you do? Well, you should have set it up to say that your initial amount would be 80. And yes, if you're wondering, will your growth factor always be 1/2? Yes, if you didn't catch that earlier, it'll always be 1/2 for this. Your exponent would be 50 divided by 124 because we're trying to figure out how much will be left after 50 years. And the half-life is, whoops, not 124 here. It would be 24 there. So we'd have 50 divided by 24 would be your exponent. When you type that in your calculator, because you can do all of that in one step. Now you got to be careful though when you're typing it in your calculator. If you're using a scientific calculator and you use the exponent button, you have to put your exponent in parentheses. So I want to make sure that I talk about that. You have to put your exponent in parentheses if you're doing a fraction that's an exponent. Okay? Otherwise your calculator will not take that entire piece as your exponent. It'll only treat the 50 as your exponent. So make sure you do that. If you got the wrong answer, that is probably why. So you should have gotten 18.9 as your final answer. Well, that's it. So again, in this lesson here, basically the only new material we learned was how to use your calculator to come up with an exponential model in this idea of a half-life. So hopefully you took really good notes, and make sure you come to class prepared to review how to deal with exponential models and half-lives.